be here. This presentation is one that is an adaptation of one that I do a great deal. Most often I do this to school children and teachers, but I think it has a wider application and deserves to be more widely known. So let me just start by showing you something really nice. You don't need to be able to read the screen if you don't. If you're finding that difficult. I did end up with a font that was slightly smaller than I expected here, but I'd just like to, if you're happy with mental arithmetic, which not everybody is, including me, feel free to pick a positive whole number. Greater than 1. I strongly recommend not picking one that's too big. In this example, I've got 5. And then once you've got that, subtract 1 from it. Most people don't find that too difficult, and that's why we wanted one that was bigger than 1, so we didn't end up with 0. So that gives us 4. Take all of the numbers from 1 up to 4 and multiply them together. So that gives us 1 times 2 times 3 times 4, which is 24. Add 1 to that. There seems to be no reason for doing this at the moment, but bear with me. And here you get 25. And you'll notice that that is a multiple of the number that you first thought of. Let's try it again. Let's do it with 6. So remember, we have to subtract 1, which gives us 5, multiply all of those together. And you'll notice here, I've actually said 5 with an exclamation mark. That doesn't mean that 5 is surprised. That's known as 5 factorial. And what that means is take all of the numbers up to 5 and multiply them together. And if you do that, you get 120. Add 1 to the answer, and that gives you 121, and say, is that a multiple of the number you first thought of? And the answer is no. So we've had a yes and a no. And if you do this several times, you discover that you get the answer yes if the number you start with is prime. And you get the answer no if the number you start with is not prime. And so we actually, we find that this was actually known to Leibniz in the 1600s. And he wrote, well, it's in Latin there, I'll translate for you. The product of integers preceding the given integer when divided by the given integer leaves 1, actually it leaves the complement of 1, of the given integer be prime. If the given integer be composite, it leaves a number which has a common factor with the integer, and so on. That seems like an awful lot of words. And at the time, in the 1600s, this was the only way that people could actually do the mathematical thinking. And this is really what I want to talk about, is the leg up on the thinking that's been afforded us by good notation, and then some of the surprises that we get from having that notation. So that was Leibniz in the 1600s, and it's known as Wilson's theorem. So to put it into symbols, for n greater than 1, a whole number, if you subtract 1, multiply them together, n factorial, add 1, then that will be a multiple of n if and only if the number you first thought of was prime. This is known as Wilson's theorem. Wilson neither originated it nor proved it. So this is typical of mathematics. In fact, Wilson was a student of, I think it's Edward Ware, and he mentioned it to Ware. He'd seen it somewhere. Ware published it it was actually known much earlier to the Arabic scholar Ibn al-Haytham, who's about 1000 AD. But he mentioned it to Ware, who then published it in 1770. It was proven not long after by Lagrange in 1771. But as I mentioned, Leibniz actually knew this as well. And actually, when Ware published it, he added, a proof would be difficult because of a lack of notation to represent prime numbers. When Gauss first came across this problem in 1800 or thereabouts, slightly before 1800, he disposed of it in about 5 minutes. He just proved it instantly using his technique of modulo arithmetic, which he was developing at the time. And he said, in our opinion, truths of this kind should be drawn from notions rather than notations. Gauss was quite scathing of this idea that the lack of a notation should be a problem. Now, it's very difficult for a mathematician to disagree with Gauss. I was at a summer school one time, and one of the exercises we had was to go through the alphabet, naming a mathematician and something they did. So with A, the obvious one was Archimedes, the Archimedes flotation principle and levers and everything else, and so forth. And when it came to G, we all as a group said Gauss, and when our lecturer said, and what did he do? We all said everything else. And you can't go anywhere in maths and science without coming across something by Gauss. Probability, engineering, just everything. It's difficult to disagree with Gauss. But I think that his comment here is not the whole story. Not least, when he said that and published his answer, he used his notation for modulo arithmetic. So I want to talk about notation, and I want to talk about the notions and the interplay between them. But I'm not going to do this in a very theoretical way. I'm going to do this in a very concrete way. Not drawn from the sort of thing that I do in industry, which is the maritime equivalent of air traffic control. It's no surprise there that there's a great deal of science, technology, engineering, and mathematics to stop this from happening. There is a technical term for this. It's called a bad thing. So I'm not going to talk about that. I'm not going to draw my examples from industry. I'm going to draw my examples from somewhere else. And I want to talk about technology, the notation. And the thing is, here is some specialist notation. And specialist terminology allows the rapid and efficient and accurate communication of information. And the more specialist the terminology, the more rapidly you can affect that communication. To the point where when you're on a boat, you don't have to tell somebody which bit of string to pull. They all have names. And you have to be able to communicate that quickly and efficiently. Notation is important, I claim. And I'm going to draw my example from here. I'm going to say, how can we describe a juggling pattern? The reason for doing this is twofold. One is it's something that virtually none of you will have had any experience of. I don't know. How many of you are willing to admit to being able to juggle at least 3? Ooh, how many can juggle 4? I did ask that question one time, and somebody put their hand up for 4 who hadn't had their hand up for 3. No, fair enough. I did ask somebody one time in a group, I said, how many can juggle 5? And there was somebody who put both hands up, because he had, in fact, at one stage held the world record and juggled 10. That was Ben Beaver, an amazing guy. So a few of you can juggle, but I don't know if you've ever considered this question. How can you describe a juggling pattern? Now, juggling patterns have names. Many of them have names. The standard patterns that people think about, where they go in a cycle, the obvious one where they go in a cycle, which is what most people do with 2, then they attempt with 3, and discover that that's much more difficult. In fact, if you look at my hands, you'll see that they are moving faster than is humanly possible, which tells you 2 things. First of all, it tells you I'm an alien. The second thing it tells you is that this is really very, very difficult. But these sorts of patterns have names. So when they go in that circle, it's called a shower, and you can have a shower for any number of balls. The more common way of juggling 3, which some of you already know, is not in that cyclic pattern, but is in fact in a figure of 8 pattern. The idea here is you take one ball and throw it, and as you wait for it to come down, you hold both of the other balls. And as this one comes down at the last moment, you can throw the next one. And if you throw it perfectly, straight up, then it will be easy to catch. And you can always just throw straight in the air so that it's easy to catch. After a while, this gets quite boring. So you bring it down, widen it out, and this is what you end up with. Now, this doesn't look like a circle. They're coming up from the middle and down on the outside. So you'll see that you get the throws from the middle and the catches on the outside. And in a sense, in fact, it is a circle. It's a twisted circle. If you take an ordinary circle and put half a twist in it, you get this figure of 8 pattern, one of the signs that we usually use for infinity. And that is the easy way of juggling 3 balls. Now, I do make it look easy. I have been doing this a long time. People do ask when I learned. I honestly don't remember, but I took it up seriously while I was at university. The more sensible question is not when. The more sensible question is why. And in my case, it seemed like the obvious thing to do after I'd learned to ride a unicycle. And I went, as you do, and I went along to my university's unicycle society, and most of the people who were there could also juggle. So I made 3 beanbags. In fact, I've brought with me tonight one of those very first beanbags that I made. This beanbag is this month 30 years old. I made this beanbag in January 1984. He only comes out on special occasions. His name is George. He's retired. And I made 3 beanbags, and I went to the juggling club, and I said, I can juggle 3. Good one. I can juggle 3, but I'd like to learn how to do 5. None of this simple stuff with 4. Let's just leap straight to 5. And they laughed at me and said, well, can you do 4? And I said, well, I've only got 3. So they gave me an extra one and said, now can you do 4? And I said, well, actually, no. And they said, all right, here's how you do 4. Now, actually, what I'd like you all to do is pick a colour, okay? This will, by the way, be much more interesting if you pick one of these colours. You don't have to. But if you pick one of these colours and watch it closely as I juggle 4, and you may notice something interesting. So what do you notice? They're not changing hands. And I said, you're cheating. They're not changing hands. And they said, well, they can change hands. But they don't have to. You can simply, always look for that word, simply. You can simply do 2 in each hand. And I said, but that's cheating. And they said, you do it. So I borrowed the extra ball, went away, and actually I came back the following week and I could do it. They were very surprised. Going from 3 to 4 in less than a week is unusual, but I've always been quite good at the things that are completely useless. And I came back, and I could juggle 4, and they said, all right, you want to learn how to do 5? Here's how you do 5. Take 1 and put it down, which sounds like the wrong way to go. And they said, when you juggle 3 the way a beginner juggles 3, you've got 1 in the air and 1 in each hand a lot of the time. And that's because you throw late. You wait for this one to come down before throwing the next one. If instead you throw early, you end up with empty hands. Never figured out why my hands click at different pitches. I guess one's just more highly strung than the other. Oh, good, somebody got the joke. Thank you. Right, so anyway, so you'll see here, my hands are empty for a lot of the time as I do that. So with my hands being empty, I can take those 3, squash them up, stick another 2 in underneath, and that gives me 5, okay? Now, I started to try to do that. And as you might imagine, it's not entirely trivial. So I stood there and I would throw 5 in the air, try to catch them and fail. Throw 5 in the air, try to catch them and fail. And I would just do that for hours. Actually, I didn't do that for hours. The general idea at the time was that it would take between 500 and 600 hours of practice to be able to juggle 5. And after 20 minutes, I was hot, tired, frustrated, and very angry because I knew what I should do and my body wouldn't do it. And I stopped and I looked around the room and nobody else was juggling 5. I found out later of the 80 very odd members of the juggling club, there were only 2.5 people who could juggle 5. And while that half may worry you, there was one person who was halfway through learning. And as you know, 1 times a half equals a half times 1. So that means one person who's halfway through learning is the same as a half a person who's all the way through learning. And if that makes sense to you, you're well on the way to becoming a mathematician, because it's this kind of crazy idea, but pushed through to its logical conclusion that mathematicians do a lot of. So anyway, there weren't very many people who could juggle 5. What do people do at a juggling club meeting? There were the people who were doing machetes and fire torches. They were unlit indoors. There were the people who were doing clubs and passing them around. But most people were just doing 3, but they weren't just doing this. They were doing 3-ball variations, 3-ball tricks. So they were doing things like this. And like this. And like this. Now, you may have noticed something about one of the balls. Let me help you. If you're worried that I'm not letting that one go, I can let it go. Let's see if I can let it go. Let's see what happens if I do this. there is a problem with this. I don't actually know what I'm doing, and I can only do it going that way. And people were doing the most amazing things with just 3 juggling balls. And I thought, that's much more interesting than trying to do 5 by chucking them in the air and failing repeatedly. And so I went up to somebody and said, show me what to do if I want to learn some 3-ball tricks. And I went up to a guy called Adam Chalcraft, and I said to Adam, show me some 3-ball juggling. Show me a juggling variation. And he said, okay, can you do... I mentioned that tricks have names. This one's called the cascade. If you do tricks in the pattern where they go up in the middle and come down on the outside, crossing over, that's called a cascade. He said, can you do a cascade? I said, yes, I can do a cascade. He said, the first trick you should learn... I've later worked out, actually, this is the second trick you should learn. But he said the first trick you should learn is pick your favorite color. I'll use the yellow one. And instead of throwing it as you would normally would, instead of throwing it in the middle, take the yellow ball and throw it over the top. Watch that, yellow ball over the top, okay? He said, learn it with your left hand. I'm going to call this my left hand, even though it's my right hand. I don't know right from left, which makes driving fun. Anyway, he said, throw it with your less good hand, because if you can throw over the top with your less good hand, then magically you can throw over the top with your good hand. It comes for free if you do it with your less good hand first. Your good hand comes for free. So that means now you can take the yellow and throw it that way, and you can throw it that way. So you can take the yellow and throw it that way and that way, which is called tennis. There was a guy in the club who used to, every time he saw somebody practicing this, he would come up behind them and go, which was very distracting. So anyway, the yellow ball over the top, not a problem, but you don't have to do it with just the yellow ball. You can do it with all of them. Now let me distinguish. The pink and the orange aren't that different, so let me bring in the green one so you can see the 3 different colours. So I don't have to do it with just the yellow. I can do it with all of them. So I can do it with the yellow and the orange and the yellow and the orange, the yellow and the green. Yeah, it is there. Okay, and throw over the top. Now I end up with this. And if you have a look at this, where's the crossing point gone? Do you remember I described the cascade as a twisted circle? If you have a twisted circle, you have to have a crossing point in the middle. But if I throw over the top, the twist is gone. Somehow I've untwisted, or as a friend of mine says, untwist my circle. Where has the twist gone? And what's happened is this hand is now going that way round instead of going that way round. If you draw an arrow on a sheet of glass and then twist it, the direction of the arrow appears to reverse. And so that's related to what's going on here. I don't have to do it with that hand. I can instead do it with this hand. And so if I do that, I end up again with an untwisted circle. But if I throw over the top with both hands, my twist is back. But now the balls are going down in the middle instead of up. And if I take a video of this and play it backwards, I end up back where I started. Right? And so there are connections and relationships between all of these patterns. I thought they were all different, but it's only one trick, one over the top, put together in loads of different ways. I didn't really realize that. I thanked Adam. I had seen a girl across the other side of the room, a girl called Alison, doing the most amazing juggling tricks, which I, to this day, cannot do, never could. They were phenomenal. I will give you a clue about what she was doing, because I went to Alison and I said, show me some 3-ball juggling tricks. She said, can you do a cascade? I said, yes. She said, you want to learn what are known as the body throws. So you want to take a ball, I'll use the yellow one, and instead of throwing it in the middle, throw it from somewhere different. And I said, well, over the top. What else will you do? She said, no, completely different. So, for example, take the yellow and throw it under the arm. Or take the yellow and throw it over your shoulder, which I can't do. To this day, I can't do that. It always goes wrong. I still try it. Or take I'm going to try it again. Oh, there you go. Or take it and throw it so it goes behind your back. Or take the yellow ball and throw it so it goes under your leg. Or you can bat it off your hand. You can roll it off your head. You can tap it off your knee. Actually, the one that I liked is to take that one and throw it under the arm. Oh, lost it. Let's try that again. Take the yellow ball and throw it under the arm, but don't do it with just the yellow. Do it with every throw, and you end up with this. And I think that's quite nice. And I also just lied to you. This is not every throw. This is only every left-hand throw. if I also do every right-hand throw, and not just for a while there, and a while there, and not just with the yellow one, back and forth, but every throw, with every ball, with both hands. And you go under here and under here and under here and under here and under here, and you can't do it at full speed. It's very, very difficult. But you can slow it down by making it more exaggerated. So if I exaggerate this, I can throw every throw under the other arm, and I end up with this. Which looks fantastic with fire torches, and they wouldn't let me do it in here. Not least, actually, it sprays burning droplets of fuel into the front row of the audience, which they don't like very much. If you're busking, other people love that. They give you lots more money if you spray fire into the front row. Because what everybody wants to see from a juggler is pain. And if not the jugglers, somebody else's will do. But no, that's not going to happen tonight. So anyway, I was writing all of these down. And I thanked Alison, ran away as fast as I could. The woman was clearly demented. And I went up to somebody else, a guy called Mike Day, and I said to Mike, show me a 3-ball juggling trick. And he said, can you do a cascade? I said, yes. He said, can you do one over the top? I said, yes. And I can do the body throws. This was a lie. I'd only seen the body throws. I hadn't worked on them yet. He said, okay, you want to learn this. And I watched him for a while with my pen poised above the paper, ready to write down what he was doing. And after a while, I said, what are you doing? And he said, it's called Mill's Mess. So I wrote down Mill's Mess. The name tells you nothing. If I actually talk to you about music and I mention a piece of music by name, if you don't know it, it tells you nothing. If you do know it, it can invoke the full richness of the experience. But you have to know the name. The name is not a notation, it's a label. In computing, they say that there are 3 things that are really hard. Cache invalidation, don't worry, technical thing. Naming things, and off by 1 errors. Right? In mathematics, there are 2 things that are incredibly important: limits, functions, and counting. People often say there are 2 things that are really important: limits, functions, and counting. And the thing is that naming things is important, but it's not enough. And when you say that this is called Mill's Mess, I'm not really telling you anything except that until you actually understand it, it looks and feels like a mess. So I said to Mike, well, what are you actually doing? And he said, well, it's 3 consecutive throws on this side, followed by 3 consecutive throws on this side. Let me help you see that. I will call the colors as they come up over here, as we get green, yellow, orange, green, yellow, orange, green, yellow, orange, green, yellow, orange, green, yellow, orange. Can you see that? Green, yellow, orange, green, yellow, orange, green, yellow, orange, order amidst the chaos. And if you have a look on the other side, we get green, yellow, orange, green, yellow, orange. It's symmetrical, so it should be the same. Green, yellow, orange, green, yellow, orange. Let's see them all. Green, yellow, orange, 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 green, yellow, orange. I'm an alien. I don't need to breathe. It's okay. So get green, yellow, orange, green, yellow, orange, green, yellow, orange, green, yellow, orange. Does that help? Actually, it doesn't help as much as you might hope, because there are actually 8 different ways of juggling with 3 throws on each side. And only one of them is Mill's Mess. So I went away and I started to write a description, very like the description that Leibniz gave of Wilson's theorem, a sheet of words, which we could then summarize when I showed you the modern notation. I wrote down 2.5 sheets of paper worth of description for a juggling trick that lasts for 1 second. And so that is then where this came from, is the question of, let me get this back, how can we do this? How can we describe a juggling trick? And I don't want to use film or video, because that's like Well, if you want to play a piece of music, especially with a polyphonic instrument like the piano or organ, and all you have is a recording, it's almost impossible, especially if it's something like Rachmaninoff or Liszt or Mozart, handfuls of notes. Finding them all and getting them all right is phenomenally difficult. Normal people can't do it. And so it is with juggling. I don't want to have film or video. I want to be able to write it down. I want a notation. Now, we have a notation for music. It's called music. We have a rotation for language. It's called writing. We have notations for dance. There are two major notations, Benesch notation, Laban notation. There are other minor variants on those. But what I want to do is have an equivalent of that for juggling. And the problem is that when you start to do this, it really is complicated. Now, by the end of this talk, you will understand how to use this to create juggling tricks. I will teach you the notation. And you will find a surprise. To do this, I need to simplify the problem. I'm not going to give you the entirety of the complexity of what we can do when we juggle, because there are just way too many possibilities. So I'm going to apply some restrictions on the kinds of things that we're allowed to do in the juggling. And there are 3 of these. The first one is that I'm going to insist that my hands don't move very much. Do you remember the diagram I had with the 2 overlapping arches, and in the middle I had throws? I'm going to insist that the throws happen here and the catches happen here. I'm going to insist that I don't cross my arms or throw behind my back or roll it off my head. Everything I've shown you that you have found entertaining is eliminated by this. Especially Mills Mess, which actually has a big arm cross in the middle of it. More, I'm going to insist that the timing be fixed. I'm going to work to a fixed metronomic beat. Now, I don't know if you'll be able to hear this. I will shut up, but if you can turn up the mic in a moment as loudly as you can, you may be able to hear the rhythm of the juggling. This is an example of what I'm not allowed to do. I'm not allowed to do that, okay? If I want to juggle that pattern, I have to do it to a fixed metronomic steady beat, which again sounds incredibly boring. So I'm not finished yet. I'm also going to insist that my hands take it in turns. You'd think if you do 2 in each hand, you'd do them at the same time, but no, I'm going to insist that they do it 1 at a time. By the way, juggling with 2 in each hand in sync is incredibly difficult because you have to throw 2 things at the same time and catch 2 things at the same time. It is remarkably difficult. That's why you take it in turns. You only need to think about 1 thing at a time. The catches take care of themselves. It's the throws that really matter. If the throws are right, then you've got it won. And let's have a look at what that means, because I can start to draw diagrams of juggling. If my hands are fixed, then I've got left hand, right hand at the beginning and in the middle and at the end, and they don't move around very much. I'm going to even simplify that. I'm not even going to have them move between throw and catch. I'm going to have the left hand and the right hand not moving. By the way, if I want to break the rule, there is how I do it. I make those lines go all wibbly-wobbly down the timey-wimey down the diagram. So I can actually have these hands move around and cross over. But I'm not going to. I said rule number 1, left hand and right hand. Rule number 2 was that the timing is fixed. And if the timing is fixed, then I can put a steady beat running down the diagram, equally spaced. And if they were raised on the paper and I ran my hand down at a constant speed, you'd hear it go tick, 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 tick at a constant rate. Here is a clue about how I can break that rule. I can squash them up here. I can stretch them out there. I can remove one. I can do all sorts of things. Rule number 3 was that my hands take it in turns. And I'm going to come back to that in a minute. I'm not going to work on that just yet. This is another lie. I can't remember who it was, but somebody said to me that one of the most honoured professions in their country was called liar to children, also known as teacher. Because when you're teaching youngsters in particular, in fact, when you're teaching chemistry every year that you go in, say, forget what you learned last year, it's all different from that. You get taught successive refinements of approximations. I'm going to pretend that this is true. It's not actually true, but if we pretend it's true, we'll find later on it doesn't actually matter. And also, if you do want to go and break a world record, I just thought I'd mention this. If you want to break a world record, there is a standard pattern for juggling, which is the one that has all of the throws identical. Now, that means that throwing in a circle is not the standard pattern, because one hand is throwing up, the other hand is throwing across. They're not all the same. So when juggling 3 balls, that is the standard pattern. World records, by the way, the world record for objects juggled is 12. The world record for balls juggled is 11. There are actually objects that are easier to juggle in very large numbers, namely rings, for technical reasons. World record for clubs is 8, for sticks is 8, for fire torches is 7, machetes is 7, fire torches while bouncing a football on your head is 7, and chainsaws is 3. So if you want a world record to break, chainsaws, no, seriously, don't try this at home. Do it at school or work, because they have much more insurance, and so you'll be fine. No, there is a standard pattern for objects. But anyway, pop quiz, I just told you this. How often are we going to pretend my hands are full for? Half the time. Right, half the time. Okay, so when I juggle, I've already given you this diagram of the left hand and the right hand and the steady beats. I need to put some juggling balls on it. I've got a framework. Let's start populating the framework. I have a skeleton. Let's put some flesh on it. So let's look at some juggling. I'm going to juggle with the orange, the pink, and the green. The orange, the pink, orange, pink, and green. There we go, in some order. Orange, pink, and green. If you watch this hand, we'll get orange. Then we'll get the pink and the green. Pink, green. Orange, pink, green. Orange, pink, green. And if you watch the orange ball, you'll see that it does visit both hands. It doesn't stay in the same hand. That's important. But over here we get orange, pink, green, orange, pink, green. And so I can start to say, what happens? Well, let's put the orange ball in my hand over there for 1 beat of time. And then, I'm actually not going to put you through the full torture of the pop quiz thing, because this is a trick question. I normally say, this is a trick question. Which color of ball goes there? None. Perfect. How often are my hands full? Half the time. And if my hands are only full half the time, I can't have a ball. See how the things that I wrote down earlier are helping me to construct this. Hands don't move, timing is fixed, my hand's full for half the time. These are things that are helping me to construct a diagram of what happens when I juggle. So there's empty and I get a gap and then the pink and a gap and the green, gap and the orange, gap and the pink ball falling off the bottom of the diagram. And now I ask you, where does the orange ball go in the other hand? Now some of you will already have a good idea about this. Let me give you a hint. It's not there. Why is the orange ball not in my hand at this moment? Because it's in the other hand. Okay, so it's not there and it's not there. So it's not there either. Let's have a look at these two places. Is it possible, is it permitted for the juggling ball to be in my hand at that point or at that point, the orange one to be in my hand at either of those 2 points? And you're saying no. Which rule gets broken? One at a time, the hands have to take it in turns. The hands must alternate, and if the hands alternate, I cannot have a ball here and here at the same time. That, by the way, also eliminates this one for me for a second reason. But I can't have the ball, the orange, opposite the green, because my hands would not be alternating then. So rule number 3 rules out these two. I've got 3 places left. Let's have a look at this one. Can I have the orange ball here? And before you say no, because everybody does, what rule is broken? My hands are staying fixed, the timing is fixed, my hands still could be full for half the time. And if you actually put the orange ball there, you'll find that, well, I've only got one orange ball here, so that orange ball is that orange ball, so I have to join it on. And then you find that this is possible if it teleports. And the thing is that I can actually do that because I do this. And if you watch the orange ball here, you'll see that it takes a long time to go that way and then zips back instantly. So this is the correct way of diagramming having the balls going in that cyclic pattern, the shower pattern. Now, of course, that's not what was happening. It's not what I was doing in a cascade, so that eliminates that one, and that leaves me here. And you can see the ball bouncing from hand to hand. Just, it really does. If I do this again, you'll see the orange ball bouncing from hand to hand. And it's symmetrical. It takes even time going in each direction. And in fact, a lot of people think of this as a wave. I think of it as the shadow of a helix. Right? If you take a helix and you look at its shadow, you'll find that it does this side-to-side bouncing thing. And of course, some of you will have done some engineering or similar, and you will know that this is the way you deal with sine and cosine. You actually deal with it as a complex exponential. Of course, if I have two of these, I have two helices. I have a double helix. What just came to your mind? DNA. And you can see bouncing from side to side. Bouncing from side. Okay, that one's blue and that one's purple, but they're bouncing. I've even got the major groove and the minor groove. Major groove, minor groove. And of course, I've actually got 3 juggling balls, so I get a cascade, a braid. And if I juggle 3 balls and walk backwards, the paths that the balls leave in the air would be braided. They would actually be plaited. And I have a friend who produces 3D printed models of juggling tricks. And you can see here, this is the ordinary cascade, the braid of the balls. You have to put the hands in underneath, otherwise it falls apart because the balls don't intersect each other. And here is actually, wrong one. Here is Mill's mess. 3 throws on that side and 3 throws on that side. Amazing, amazing stuff. I did put in my order for Christmas, but I didn't get one. Santa let me down. So anyway, if we have a look at a single flight of a juggling ball, we can see that it's thrown from over here, and we can follow the ball as it travels to the other hand, and it gets caught down there. And ask, how long does that take? How many beats of time is that? 2, right? So that is time of flight, 2 beats, don't care. Why don't I care? I don't care because that's the time from a throw to a catch. And the thing that really matters in juggling is the throw. If the throw is perfect, all you have to do is stick your hand in the right place and the catch will happen automatically for you. So it's the throw that matters. And if we look at the time from throw to throw and ask how many beats of time is that, what answer do we get? 3 beats, the same as the number of balls I'm juggling. And that is not a coincidence. It turns out that when you juggle the standard pattern with any number of balls, not the time of flight, the cycle time, the time from throw to throw, is always equal to the number of balls. There is a very elegant and simple proof of that, which is simply that the balls must take it in turns. So if you've got n balls, they will each be thrown every nth time, so it has to be n beats between throws. So that means that my cycle time has to be 3 for 3 balls. The flight time is always less to allow for the time in the hand. And under our assumption of half the time, that means that it's 1 beat in the hand, so that will be 2. So if I juggle 4 balls, what should these numbers here be? 3 and 4. And I want to pause now, because what you've just done is used the notation to understand the notion. I have a notation here for what's going on when I'm juggling the balls. And you have just predicted what will happen when I juggle 4 balls. Now, there are only about 3 of you who had your hand up when I asked how many of you can juggle 4. So for the rest of you who don't juggle 4 balls, you are making predictions about something you can't do and probably have never really watched. And if we have a look at this, you'll see that we get green, purple, orange, blue, green, purple, orange, blue, or pink, green, pink, orange, blue. And I've only got 1 green juggling ball, so I have to join that on. I have to join that on. The orange ball, I have to join on. I have to join on. And if you watch me as I juggle 4 balls, if you watch the left hand, you will see the 2 balls bouncing over each other. And here, of course, they're bouncing over each other in time. If you turn it side on, you can actually have them bouncing over each other in space. And I can mix up space and time. Distance divided by time is speed. If I have non-zero speed, I can have the balls play leapfrog over each other in space. I can actually have them bounce over each other in space. That's just silly. All right, so they're playing leapfrog, but they're playing leapfrog in time. And if you look at this, you'll see that the green ball, how long does that spend in the air? Well, it's that gap plus that hold plus that gap, and that's where the green ball comes down, plus an extra hold. It will be 3 for the flight time and 4 for the cycle time. So what do you think these numbers are going to be? 4 and 5. By the way, you should never trust a pattern unless you have a reason to believe why it must be happening. I have dozens of examples of that. But I've already given you a proof that that number should be 5. It's a hand-wavy, informal proof about these things. We can test this. Okay, so here we go. Time of flight, 4 beats. Let's have a look. Hands full half the time, hands taking it in turns. There's a throw. Count down 4 beats. At that moment, that is the time when the ball will come down. Which hand will catch it, left or right? The right hand. It has to be the right hand because it's the right hand that's empty and needs a ball to come in. The left hand already has a ball. That's a throw. So that means that the ball has to come into the other hand. When you juggle 5 balls in the standard pattern, they must change hands. You don't have a choice. And so we can join that on. The ball changes hands. All the balls change hands. All the balls change hands. And if you pick out one of those, you will still see it bouncing from side to side. Now, we should verify that there are 5 balls in this diagram. Simple way of doing it is to colour them all differently. That's quite tricky. Getting 5 colours that show up clearly on this sort of thing is quite hard. I suggest that we take a photograph. And I think of a photograph in a slightly odd manner. I think of a photograph as a barrier in time, and things pass from the past to the future through the photo, leaving an imprint as they go. Like a cartoon character running through a wall and leaving their silhouette as a whole. So it is that the balls have to pass through a barrier, 1, 2, 3, 4, 5 of them, as they travel from the past to the future. There really are 5 balls here. So that means that those numbers are right, which is good. Okay, so that, by the way, tells us what's going to happen when we do silly numbers. 201 balls means that the flight time should be 200. That means if you can juggle at 20 throws per second, 20 hertz is inside the limit of human hearing. You would be vibrating so hard you would hum. Okay? You still need to throw the balls at over 170 kilometers an hour, 109 miles an hour. Miss the other 200 that are already up. No, you're not going to do that. But what happens as the numbers get smaller? I mean, what happens with 2 balls? What will these numbers be? 1 and 2. So those numbers should be 1 and 2. So that means that juggling 2 balls actually looks like this. If you do it slowly, if you do it at full speed, I juggle 5 balls at 4 throws per second. That looks like this. At which stage most people go, what's the point? Actually, this is surprisingly difficult. When I teach people to juggle 3 balls, I get them to do this for a little while. It's very difficult to do. And whenever I say that, I've just seen someone, there's always someone in the audience who sits there going like this. And I say, it's harder with the juggling balls there. All right? If you don't have the balls, it's really... Look, I can do 17. No, it's surprisingly difficult to do 2 balls. Anyway, what happens with 1 balls? What are these numbers going to be with 1 ball? 0 and 1. 0? Yeah. If you've only got 1 juggling ball, the time it spends in the air must be 0. Otherwise, you can't fill both hands half the time. So here we are. This is full speed 1 ball juggling in the standard pattern. By the way, this one, uniquely amongst the juggling tricks I'm doing tonight, this one I can do in super slow-mo. Okay, so that was silly, but I just had all of you silently watching me pass a ball, failing to pass a ball really slowly from one hand to the other. All right, so what do you think comes next? What do you think this number down here has got to be? That's got to be a 0. What do you think this number has to be? 0, -1. I get both answers. I always get both answers. And the people who say 0 know that -1 does not make sense. And the people who say -1 are saying that's the only thing that can make sense. Let's see what happens. Because that is time travel. It says you throw the ball and it comes down earlier. That would be a great trick. So I'm actually going to do it. I am going to perform the time travel of juggling balls. And I'm going to do this by doing a pattern of patterns. I'm going to abandon the standard patterns, and I'm now going to do 4 balls. Actually, this is the standard pattern with 4 balls, each ball thrown every 4th time, and you can see that. So you get the orange 2, 3, 4, orange 2, 3, 4, orange 2, 3, 4, orange 2, 3, 4. So each ball is thrown every 4th time, and I can write that down just by saying do a 4, 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 do a 4. Okay? This is a notation for a juggling trick. And this is a notation for a juggling trick that's been known for over 100 years. We've known that it's possible to do 4 balls and then suddenly, without provocation, throw one as if juggling 5 and throw one as if juggling 3. So it'll be the orange high and the yellow low, and see if you can see both of them go. Orange high, yellow low. I'll count down. 3, 2, 1. High low. Did you see that? Let me do it again. Yellow high, orange low. 3, 2, 1. High low. And again, high low. Whoops. Well recovered. And again, yellow high, green, yellow high, orange low, yellow high, orange low. So in the middle of juggling 4, I can do a 5 and a 3. In the middle of juggling 4, this has also been known for over 100 years. You can do a 5, 5, 2. That one, by the way, is known by its name where it's inherited from clubs. It's known as a triple single because 5s are normally done on triple spins and singles are normally done, 3s are normally done on single spins. So you do a triple single in the middle of 4 balls. Now I can do a triple pause. Because I'm going to throw one high and crossing, that's a 5, high and crossing, that's a 5, and then a 2. I'm not going to do this, okay? I'm just going to hold it up and show it to you. So I'm going to do orange high, green high, and yellow as a hold. Again, counting down, 3, 2, 1, 5, 5, and there's the 2. And again, this time, green and pink going high. Okay, green and pink, and there's the yellow. Pink and orange, and there's the yellow. And if you, lost it. If you're worried that the yellow hasn't had a chance to play, I can send the yellow one around instead and carry on with the others. So I can do a 5, 5, 2. Well, let me ask you, what comes next? What do you think? What do you think the last number has to be? 1. And what do you think all the other numbers are going to be? So what do we get? We get 5, 5, 5, 1. And when we first wrote that down in the mid-1980s, as far as we can tell, nobody had ever done it. And when I took this to the British Juggling Convention, there's a British Juggling Convention. When I took this to the British Juggling Convention in 1985, people quite literally sat at my feet for 4 days trying to learn how to do it. Like trying to learn a poem by just listening to someone recite it. It's really hard. They did not know the notation. So let me show it to you. In the middle of juggling 4, I need to do high and crossing, I need to do high and crossing, I need to do high and crossing, and then zip one across the bottom. By the way, at the European Juggling Convention, 4 months later, people from America were trying to teach it to me. Because it was the new trick worldwide. So here we go. Green, pink, and yellow going high, and the orange zipped across the bottom. 3, 2, 1, 5, 5, 5, 1. Well, that's pretty tough to see. Let me do it for you constantly. I'll try. Here we go. 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, and drop back to 4. Superb practice for juggling 5, because 3 out of every 4 throws that you do is exactly the kind of throw that you need to learn to juggle 5 balls. But it's so much easier because it's only 4. And by the time you're trying to do 5, juggling 4 is not that difficult. And the amazing thing is that you predicted that purely from the notation. And this reflects exactly what happened when Dirac in 1928 predicted the existence of the positron, purely from the mathematical notation for what was going on. And it was 5 years before it was actually seen. Actually, it was seen in 1929, but they dismissed it as an aberration. It was finally confirmed in 1933. 5 years But it was from the notation that the notion arose. And thus came a new discovery. And it's exactly the same process as I've just led you through here. And to be honest, I don't actually care what comes next. 5. Go on. 5. 0. And that's time travel. So you have predicted the existence of a juggling trick that requires time travel. So I will do that for you, because this is cool, right? The question is, how can you do it? Well, here we go. Do you remember rule number 3? Hands alternate. Very good. I'm impressed. Hands alternate. So there we go. And I do a 4, and then I do a 5, 5, 5, 5, 0, and then I go back to doing 4s. Now, the 5, as you remember, changes hands. The 5 changes hands, 5 changes hands, 5 changes hands. The 4, as you remember, bounces in the hand. So the 4s bounce in the hands. How often are my hands full? Half the time. I need a juggling ball here. Its cycle time will be 0. What will its flight time be? -1. It has to go backwards. So actually here, every throw has a catch, every catch has a throw, the whole thing seems to join up, the whole thing seems to be consistent. Let's count the balls. 1, 2, 3, 4. Let's count the balls. 1, 2, 3, 4. Let's count the balls. 1, 2, 3, 4. By the conservation law of juggling equipment, there should be 4 balls everywhere in this diagram. Let's count them here. 1, 2, 3, 4, 5. What do you add to 5 to get an answer of 4? -1. This works if that's a negative ball, right? It's an anti-ball. And what we actually have here is mutual creation and annihilation of a ball-anti-ball pair. All right? And the thing is that the problem with trying to do this is it actually requires mass. Right? Because antiparticles have positive mass, so this requires 2 lots of positive mass. So where do we get the mass from? Well, what's the most famous equation in the world? E equals mc. It should be e to the I pi plus 1 equals 0. It's not. It's E equals mc squared. E equals mc squared. That means that energy and mass are interchangeable. So this requires energy. But where do I get the energy from? Well, just as there's a quantum uncertainty principle between position and momentum, there's a quantum uncertainty principle between energy and time. And if you've got a very small uncertainty in the time, which we have because I know exactly when the throws and catches are happening, and we've got a very large uncertainty in the energy. So we can borrow from the quantum uncertainty in energy to create a virtual ball-anti-ball pair so long as they mutually annihilate each other within the uncertainty period, as long as you don't do it next to a black hole. One might fall in, other pop out, Hawking radiation. We can use the quantum to do this, right? Okay, that sounds crazy, but actually that is what Dirac did, and the positron is an anti-electron, right? And they've determined that in the quantum vacuum, particles can be thought of as winking in and out of existence constantly. We've just seen the same ideas here in an admittedly trivial context that are used to make laser beams and computers. And these ideas arise in part from the notation. It's not independent of the notions. And it's what is so powerful is the interplay between the two of them. In truth, I actually end up with an empty hand at this moment. I have no idea where these spots come from. In truth, I have an empty hand here at this moment because I've thrown all 4 balls in the air, and so that means that I don't have a juggling ball at that moment. Fair enough. But if you listen closely, you will hear the small thunderclap of the ball, anti-ball pair, mutually annihilating each other. So here we go. I'm going to start pink, green, yellow, and orange, but, frankly, who cares? Starting with the pink ball, counting down. 3, 2. Oh, so annoying when I don't get it right. Here we go. Let's try it again. Orange ball first. And at that moment, the hand is empty when it should be full. By the way, in physics, we know that light can be thought of as a particle and a wave. They're still wondering what gravity is. And some people think gravity travels in waves. Every juggler knows that gravity travels in waves. That was just a sudden gust of gravity. So anyway, so the idea is this is really cool stuff. We can actually do 5, 5, 5, even though this looks like it requires an antiparticle. The theory is simple and consistent. If we allow these bits of craziness, the notation can guide our notions. And then we can explain our notions through the notation. And on the way, we can discover new things, some of which are actually useful. And that's what makes me do a little happy dance when I do this kind of stuff, because it's bonkers, but sometimes it's useful. And the thing about maths, the thing about pure maths, is you never know which bits are going to be useful. And you pursue it because it's bizarre and interesting and inspiring and engaging. And sometimes it comes back to reality, sometimes it doesn't. You never know which bits. You never know which bits of notation will give you new notions and potentially lead to new discoveries. And that can be really exciting. And I hope this little journey that we've been on, you've been able to experience some of the fun that you can get as you find those new discoveries in something that you've never done before. Thank you very much.